to introduce Gabe Givens. He's a PhD student in physics here at MSU, and he's part of my research group. And he's been doing a lot of work and research into fermionic mappings, which are a crucial part of algorithms that try to simulate physical systems on quantum computers, particularly fermionic ones. This is relevant for chemistry, for nuclear physics. And it sounds like we'll learn some techniques for doing this, some traditional techniques and perhaps some lesser known ones as well. So we're very excited to have Gabe speaking with us today. And without further ado, take it away, Gabe.
Great, thank you. So it's known that people like Dean Lee in his research group do nuclear lattice simulations where they put fermions on a lattice to compute properties of nuclear matter. So what we want to figure out is how can we do this on a quantum computer? So this is a picture representing one way to number a grid of fermions, and the importance of this will become clear later. And I will give a bit more introduction of the problem that we're trying to solve, and then I will talk about several methods, including the older Gordon-Wigner mapping, which Nathan talked about last week, and then other linear transform mappings related to that. And then I'll introduce a couple modern methods which are more efficient, although with more difficulty in implementing them. So we consider a Hamiltonian of this sort of form. It's in the second quantized form with creation and annihilation operators like we saw last week. The first term is on a single site. You can see it's basically number operators for like spin up and spin down particles. And then the second term is hopping terms from site I to j. Often in nuclear physics, we only care about hopping between nearest neighbors, but most of what I'm talking about works generally. And this is a reasonable Hamiltonian to think about because it's similar to what you get in a pineless effective field theory with no three body terms. And basically what we want to do is take some initial state and find its time evolution. But I should say, feel free to raise your hand with questions at any time, or if you're on Zoom, just shout at me. I should hear you.
So you don't have to look.
And the methods I talked about have applications outside of just nuclear physics, really just any quantum system. There are a lot of papers applying this for nuclear chemistry, where instead of fermions, it's more the electron orbitals, but it's fermion modes, so most of the math is the same. So this might look a little familiar if you were at the talk last week. There is a method to implement the exponential of an arbitrary Pauli string on a quantum computer, because if it just has one Pauli gate, e to the I theta y, it's a rotation operator. So this is basically just a multi-qubit rotation operator. And we use the Rx and Hadamard gates to rotate into the Z basis so that we can then just use a single RZ gate to apply all of the rotations. For the rest of the talk, the details of this don't matter. It's just really important that this circuit exists. And also that the number of 2-qubit gates, which are currently the most expensive part of the quantum computation, the most difficult part. So the number of 2-qubit gates depends on the length of the Pauli string. So in general, we want to keep the strings short. So then if we have a Hamiltonian that's a sum of subterms, we can use a Trotter approximation. So what this basically means, if we can write our Hamiltonian in terms of a sum of strings of Pauli operators, using the Trotter approximation gives us a product of circuits like we saw on the previous slide. So basically, the big question, which I'll be discussing for most of the talk, is how do you take a Hamiltonian, like the one I showed, and write it in terms of Pauli strings on qubits? So it's taking the creation and annihilation operators on fermions and turning them into a string of Pauli operators on qubits. So the simplest method is Jordan-Wigner, and you just say that the qubit I stores the occupation of fermion I. So it's just a really nice, simple, direct one-to-one correspondence. And you can recall that the fermion creation operators look like this, where this is a creation operator for fermion J. So fermion J is in the 0 state. It takes it to the 1 state and applies the parity term based on the parity of all of the previous lower index fermions. And if fermion J is in the 1 state, it kills the entire state vector.
Is your screen share?
Oh, is it not? Sorry about that. Yep, I didn't realize that we hadn't set that up.
No, I forgot to.
And
Yeah, it's
okay,
good now, I think.
and get rid of that. Okay,
Cool, we're good, yeah.
and the fermion creation and annihilation operators anti-commute. So for those who are a little unfamiliar with anti-commutators, this means that AJ times AK equals negative AK times AJ. So now we can construct the equivalent operators on qubits. So I've written it a few ways. One is in terms of Rosen-Ketz, where you can see it takes the 0 state to the 1 state. And if you input the 1 state, it kills it. I also have them written as matrices and in terms of the Pauli matrices. So this is nice that it has many of the properties. Let's see.
Can I ask a real basic question from 2 slides back? You kind of threw me for a little. I understood the first line when you have the creation operator.
Mhm.
So it's the 0 to 1.
Yes.
That's a parity. But when I expected the second line to just take the 1 and just turn that 1
Okay.
to 0.
Okay, yeah.
Parity.
That's a good question. Yeah.
The whole thing.
So the annihilation operator, which is the AJ without a dagger, would do exactly what you're saying. This is also a creation operator. Sorry, he saves space, he just listed the creation operator. Yes?
How would you handle that doing this? Because you were dealing first with.
Oh, yeah, so, yeah, for this, I'm mostly just ignoring spin. You just go back and add it in later. So just, yeah, for simplicity, I'm ignoring that for now. Thanks for the good questions. So this is nice, but they don't anti-commute. So we aren't done. And because of not anti-commuting, they don't give that phase factor, the negative sign that sometimes appears. So we note that our qubit raising and lowering operators anti-commute with the Pell Z operator. And that means that we can add a string of Pell Z operators on all qubits less than J. And here sorry for the lack of space, but give an example to kind of give the intuition of why it works, because the X and Z anti-commute. So the Z0 anti-commutes with a Q0, and you get similar things with other numbers.
Could I ask why, do you have a nice reason why they don't anti-commute? Like what is their anti-commutator? Is it easy to see? Yeah, no worries if
Yeah. But anyway, we found a way to fix our qubit operators to have the anti-commutation that we need. Unfortunately, they are non-local operators because they operate on a lot of qubits that are not the ones that are not just immediately corresponding to the fermion that we want to create or annihilate. And they have size O of n, where n is the number of qubits. So for large systems, this is inefficient. So we can consider instead the parity mapping. So instead of storing the occupation number, we store the parity, which we recall that was what was causing the problems for us, the parity that causes negative sign, which is why we needed the string of Z operators. So if we instead just store the parity on the qubits, we can just use one Z operator. So our qubit creation and annihilation operators get modified a little bit to account for this. But when we create or annihilate fermion J, we have to update the parity for fermions with indices greater than J. So we actually haven't solved the problem, we've just moved it to having an X string on one side instead of a Z string on the other side. But fortunately, discussing this is useful for some intuition for making a generalized mapping based on a linear transformation. So we can let F be a vector of the fermion occupation numbers, or ones and zeros, based on whether each site or other fermion mode is occupied. And also define a vector of the qubit states. So now we just define some invertible n by n binary matrix A. And that A defines the transformation between a vector of fermions and a vector of qubits. And all math, of course, is done in F2 or mod 2 to keep with ones and zeros. So the simplest possible case is a Z identity matrix where you get Jordan-Wigner. Then the parity transformation uses a lower triangular matrix. So you can see that the qubit 4 is the sum of all 4 fermion occupation numbers, which is how the parity is defined. And you can obtain the inverse matrix through row reduction.
Is this saying that, because you could come up with a nonlinear mapping, right? We're just sort of considering a class, maybe not all classes.
Yes.
Or is there like a reason it has to be a linear mapping between F and omega? I see how I can see how it's a generalization. I just wasn't sure.
This is
like,
I think just a generalization to linear maps.
Yeah. Okay.
But we will in a few minutes discuss a particularly interesting example of a linear map that does give improvements over Jordan-Wigner. So we can start thinking about some of the problems that we had with creating the Jordan-Wigner and parity transformations. So if we change the occupation of fermion J, what qubits do you need to update? Because in Jordan-Wigner, there was none, well, other than J itself. Parity, it was all qubits greater than or equal to J. And it's the qubits corresponding to non-zero entries in the jth column of A. And we call this the update set. So from this, can you figure out what the update sets are for the parity transformations? I guess I already kind of told you. But does it generally make sense to people why that we get the correct update set for the parity transformation?
So the non-zero entries are the.
Yes, so the ones. So, so.
What do you mean by updated?
Flipped between 0 and 1, whichever way. So it's
when you apply a dagger or
we apply so changing the occupation of the jth fermion mode means we are applying AJ or a dagger J. So if it's fermion 2, then 2, 3, and 4 need to be updated in the parity mapping because we've just created or annihilated fermion 2, and then fermions 3 and 4 need to be updated to store the parity correctly. So for Jordan-Wigner, that being said, it's just J parity, as we discussed. And like we needed in the parity transformation, we apply X gates to qubits in the update set to change their state. So now the parity set. In Jordan-Wigner, we needed the Z string to measure parity. And we generalize this to what we call a parity set. And it's a little unintuitive how you get this result, but it's basically that the matrix R calculates parity, the lower triangular matrix, and then A inverse is transforming from the qubit basis back to the natural fermion basis. So basically A dagger is basically because you're taking the qubits and transforming it to a parity basis. But anyway, you can take the non-zero entries in row J of RA dagger, that gives you the parity set. And so for the parity transformation, as you can see, for fermion I, the parity set has qubit I minus 1, because that stores the parity. And Jordan-Wigner, you have to add up the parity yourself. with the Z strings. And because A and A inverse are the identity, this is the correct matrix to use for Jordan-Wigner. And like the Z strings in Jordan-Wigner, you apply Z gates to the parity set. Then there's finally the flip set, which is not the best name with its usage now. There are a couple of different conventions for these sets. I'm following one specific one. But basically, the flip set is what qubits you need to add up to determine whether fermion J is occupied or not. So it's just going from qubits to fermions. So you're just using A inverse. So kind of way to understand what it's doing is looking here at number 4. This qubit 4, stores the parity of all 4 qubits. So then by just adding the parity of qubits 1, 2, and 3, you cancel it out and recover the occupation of fermion 4. So once we have all these sets defined, we have the generalizations of our fermion creation and annihilation operators in terms of Pauli strings, where you apply X to the update set, I plus or minus Z acting on the flip set based on whether it's creation or annihilation, and Z's to the parity set. And it's possible to show pretty easily that these recover, the X plus IY that you get in Jordan-Wigner because of the X times C that you have some things that are in multiple sets. So we've now shown arbitrarily many ways based on the linear transformations. I guess not arbitrarily many since it's a finite matrix with only zeros and ones, but many ways to convert the Hamiltonian into strings of Pauli matrices. Unfortunately, so far, all of them have length O of n, where n is the number of fermions. And turns out there's a nice hybrid kind of compromise method between the two of them that scales as O of log n, which is the Brodby-Kitaev transformation. And it obtains this using a binary tree structure. And you can recursively generate the matrices. And here's an example of what it looks like with 8 fermions. And we can see that like the update set for fermion 4 has qubits 7, 5, and 4. And because of the binary tree structure, the size of the update set scales as log n instead of n. And for the same reasons, the parity set also scales as log n. Are there any questions on this slide before I move on?
So what's the rule for having ones?
Yes. So you start with a 1, and then you have blocks. So 2 blocks get the previous matrix, and then you have zeros, but then a row of 1s along the top.
Okay.
So because the last qubit, I think, it stores the parity of all of the fermions, but then you have various partial parities. So then like all of the here even numbered qubits just store the parity of a single fermion. So some rows are like Jordan-Wigner, some rows are like parity.
So it has a fractal like structure to it.
Yeah. Yeah, because literally when you go to the one with 16 rows, you take this matrix and copy it down here, and then just extend the ones across the top. So now we can talk about more modern methods, which are more efficient, such as auxiliary qubit mappings. And Joe, I just noticed there are a couple chat messages. Is there anything?
Those are okay ones.
Okay,
They're all. This is a natural place for questions.
oh, yeah, it is a good point for questions.
You have questions? So you mentioned there's only, offhand, there's a finite number of these possible mappings because it's Z2 and
Yeah,
I was just realizing it's also true for just arbitrary mappings, right? Like the number of mappings between n bits and n bits is very large but finite. So
yeah, I guess so.
it's amusing to me that you could imagine just kind of brute force trying a lot of
Yes.
these different possibilities.
Except with auxiliary qubits, you're increasing the number of qubits, and you can do that arbitrarily. Obviously, you wouldn't want to make it too large.
Yeah,
but-
so everything you talked about before was same number.
Yes.
N qubits, n fermions, right?
Yes,
Cool.
and yeah. And so the auxiliary qubit mappings is basically just a class of methods where you add additional qubits to store data to make the strings more local, meaning that you aren't using the long strings of distant qubits. So this is a nice picture from one of the papers that shows the first step is the Jordan-Wigner transformation. And this is using the S pattern of numbering qubits. So you can see the long Z strings connecting the qubits in hopping terms. And the main principle of an auxiliary qubit mapping is that you add in the auxiliary qubits, and then you can cut out the strings. So it's just fading away to cancel the long Z strings. And the way you do this is by storing the parity of sets of qubits in the auxiliary qubits, so that instead of visiting all of the qubits to compute the parity, you can just visit an auxiliary qubit that has a parity stored on it. But in my investigations of these methods, it's kind of unclear to me how much the need to update the auxiliary qubits offsets this advantage. It definitely improves locality, but yeah, there are some additional costs.
This is a silly question, but when would the parity get updated? Is that not set by the your particular mapping?
Well, I think it would be that you,
Or I guess, sorry, it's dependent on the application number.
yeah,
Okay, yeah.
it's some fermion. It's and yeah, so this is going back to Jordan-Wigner with a nice identity matrix mapping between the fermions and the qubits. And of course, you could use the other linear mappings. It's just easiest to understand this with Jordan-Wigner. But it's basically, yeah, if you updated this fermion, this auxiliary qubit would probably also need to be updated. So now the other main class of methods these days often have constant scaling in the number, or claim to have constant scaling in the number of fermions. And these are based on Mayuran fermions. So there's a mathematical trick you can do to split some fermions into two sets, split a fermion into two Mayuran fermions. this is just a purely mathematical thing as far as we are concerned. And they satisfy slightly different anti-commutation relation. And the interesting things is that the Majorana operators are the creation and annihilation operators are the same. Gamma equals gamma dagger, and also that Majorana fermion squared equal 1 are the identity. So from these, we'll just define what we call edge and vertex operators, which are capable of generating any fermion operator that preserves parity, which our operators do. Some of them just depended on whether fermions are present on a site, and others just move fermions from one site to another, so it preserves parity. So like the hopping term can be written like this in terms of the edge and vertex operators. So the question is, why did we define them and why do you call them edge and vertex operators? So we're going to define a graph. We place the fermions on the vertices of this arbitrary graph and create edges corresponding to the edge operators in our Hamiltonian. So for many of the cases we think about, this is just going to be a square lattice, but this in principle works with any sort of graph. And we can define the degree of a vertex by the number of edges that touch it. And we put half of the degree of the vertex as a number of qubits on each vertex. And then for each vertex, we'll define a number of local Majorana operators equal to the degree. And these are not to be confused with the fermion Majorana operators, which you talked about earlier. They have the same sort of math. They have the same anti-commutation relation, although they will commute with the local Majoranas for other vertices. And then there are multiple ways to encode them. This is a nice figure. Shows the first one has an X gate on the first qubit, second one has a Y gate on the first qubit, and the third one has a Z gate on the first qubit and the X qubit on the second. This is apparently Jordan Wigner. I'm not entirely sure how that works, and I'll need to look into that more. You can also use methods like Ravi-Kitaev for more efficient encodings. Well, this is more intuitive to explain. And now we need to encode the edge and vertex operators in terms of these local Majoranas, which are Pauli strings. And basically, this will soon become more intuitive of what's going on. So this is an example of what you'd get with an edge operator. You have some phase factor, and then you're just connecting the Majorana fermions, the local Majorana modes corresponding to the two fermions. And with the mapping, you know what Pauli string that corresponds to. And here's another example. And the edge operators in the Jordan-Wigner encoding end up just being a Z string calculating the parity of the local Majorana modes on that site.
Gabe, quick question.
Yes.
Maybe I'm the only one in the room, but I've never seen that notation with the circles and circles inside a circle.
Okay. Okay, yeah. So, yeah, that's something we probably should have explained better. Thank you for the question. So each big circle represents one of the vertices of our graph. And then we can see the edges connecting them. The little circles, again, here are on the left side are the local Majorana on each vertex. And then on the right side, we have the qubits. So I'll get to you in a minute. I'll just try to go through the edge operator a little more clearly. So in our Hamiltonian, we have a hopping term between fermions J and K. So we need to use the edge operator. So we have a minus sign or not. And then we have the local fermion operators. So if you just look at this particular fermion vertex, we see that there are 8 local Majorana modes. Each one corresponds to an edge connecting it to a neighboring fermion. So the 2 Majorana modes, local Majorana modes that we need for this edge operator are the 2 that correspond to the link for the hopping term that we care about. And then we have the encoding of that local Majorana mode into Pauli operators on the qubits corresponding to the vertex, corresponding to the fermion. Yeah, this is a bunch of layers of abstraction, so it is kind of complicated. So there's a question back there.
I think I get it. So on the right side, we have the fermions, on the left side, the Majorana representation.
Well, no, on both sides, the big circles are the fermions. On the left side, the little circles are the local Majoranas. On the right side, the little circles are the qubits.
I'm glad you asked that question. I'm glad you asked that. Okay, that makes sense. Thank you. So I think I don't quite get, maybe, okay, so I don't get the upper index, P and Q.
Okay, yeah,
Is that just
yeah.
about the problem or about you? You know what I mean?
Yeah, so those are, it's like, K is the pth neighbor of J,
Okay,
J is the qth
So
neighbor
order
of K.
that, you know, there's
Yeah,
some-
so it's just, how we label the Majorana modes. The lower index is the fermion that it corresponds to, and the upper index is which local Majorana on that site it is. Yeah, they're not exponents. Yes?
And when you say there's one side that has 4 frames, what do you mean by one side?
So I don't think they said quite that, but I'll just go over it again. So each vertex on the graph corresponds to one fermion or fermion mode in the physical system that we care about. And then each vertex has associated to it, in this case, 8 local Majoranas that are just a mathematical tool to construct this encoding. And then each vertex also has 4 qubits, which are what the quantum computer is made of. So we need to just figure out what operators you put on what qubits to reproduce the physics.
And the number of smaller ones depends on the connectivity to other fermionic.
Yes.
Okay.
And yeah, this is an example that's very connected, but it's just a good illustration. And as you might have been starting to think about from what we were just saying, it's possible to omit some of the edges from the graph. So it's just the trade-offs of connectivity, and that you'll need a product of edge operators. So basically, if you don't have this link, you'll need to like go over to this vertex and then down. So you need 2 edge operators instead of 1. But because of reducing the number of edges, it reduces the number of qubits required. So in many cases, it can simplify the problem. And the method, as I described it, only works with an even number of fermions. And you can add auxiliary modes to have an odd number of fermions, just add some extra complications. And as far as I can tell, just setting up the initial state on the circuit is more difficult than for the linear transform mappings or AQM. And for the paper I was getting a lot of that from claims that the auxiliary qubit mappings are actually a special case of the local encodings using Mayuran fermions, although they don't really provide an explanation. So it might try to understand that more. But it's very interesting how this completely different picture might actually be describing everything that we'd already thought about. And thank you for attending, and here are the most useful resources that I consulted in preparing this presentation.
Yeah, all right, thank you, Gabe. We have plenty of time for questions, so if you have any questions. Maybe I'll get us going. So you had, we were all staring at that diagram for a while. We had before. Could you go back just a couple slides to that?
Of course.
The local encodings one. Yeah. So yeah, sorry if you've already said this, but why are there less qubits than local fermions? Here you have 4 on the right side.
Yeah, it's just how I'll go back again. Just how it was encoded. It's, I guess, because of using the X and Y on each qubit with anticommutation, you can assign 2 local local Mayuranas to each qubit.
Is it sort of like Mayuranic fermions have less information in them? Because I'm feeling like you need it's like I'm thinking you'd need the same number of qubit operators as you would create Annihilation. What's wrong with that?
Yes, but yeah, I think it is about the Mayuranas kind of have less information because you need 2 of them to make a regular fermion.
Oh, okay.
And it's just the mathematical tool that just helps with understanding in terms of pretty graphs like this. I think that's one of the main reasons they talk about the Mayuran fermions.
Do you think it's nice that these operators are Hermitian too? Because that kind of seems to lend itself to quantum computing a little bit more. The Mayuran operators are Hermitian. I mean, is there
maybe? And
anything to that?
Yeah, and also some of you might be familiar with the toric code. Some of this looks with the edge and vertex operators might look a little familiar. It is using a lot of similar principles. Just the toric code is for error correction, so it's trying to store data non-locally. Here we're kind of trying to do the opposite of trying to keep things as local as possible. So I think that's another reason that there's existing literature using this sort of math.
Record
Yeah,
progress.
I think I hear it. Oh. Okay, well, if not, let's give Gabe another round of applause.